I'm Laurie Middlemiss, and I'm just going into the second year of my PhD at Sheffield University, and I'm working on the performance optimisation of sodium-ion batteries. And this project's in collaboration with Faradian, which is a battery research company located in Sheffield, nearby to university. So, interest in sodium-ion battery stems from three current major limitations with lithium-ion technology. The first of which is sustainability. So, lithium can only be found in certain regions on Earth, and in fact over 70% of current known deposits found in a concentrated area in South America, known as the lithium triangle. And there's a realistic possibility that by the end of the century, with things like the advent of the electric car, that demand may surpass supply. This scarcity of lithium reserves also has an add-on effect that the price of the metal is increasing, as indicated by this graph on the left here. And lastly, there are also concerns around safety. So lithium-ion batteries are susceptible to overcharging, which can lead to overheating, and in some instances, firmware runaway. This image is of a laptop undergoing this process, and if you think back to last year, Samsung had to recall a certain model of mobile phone because of this problem. So sodium-ion batteries seems a favourable alternative because sodium can be easily extracted from seawater, and is over 1,000 times more abundant in the Earth's crust. When commercialised, sodium-ion cells are predicted to be around a third cheaper than lithium-ion batteries. They also become self-heating at a higher temperature and heat at a lower rate, so considered safer. So over the past few years, there's been several materials appearing in literature and patents, with energy density starting to rival those of lithium-ion battery counterparts, shown by this graph here. And in fact, Faradian have even been successful in developing a cathode with specific capacity exceeding that of the well-known lithium-ion battery chemistry, lithium-ion phosphate. However, currently what is limiting sodium-ion batteries from reaching commercialization is their cyclability, so ability to achieve these high capacities and hold them over time. So the overall aim of my research project is to identify the fading mechanisms that occur in sodium-ion cells, and hope to be able to overcome these to enhance performance and create an ideal battery. So I assembled and tested some cells using materials provided by Faradian, and you can see that while they have a reasonably stable discharge capacity and Coulombic efficiency, the capacity appears to be somewhat limited. So I'm only getting around 125 milliamp hours per gram, but I should be able to theoretically get about 150. So I want to determine what of my cells is limiting this from being achieved. And for this, I'm going to use a technique which allows me to characterise the electrical properties of sodium-ion batteries, as well as the resistive losses occurring inside them, which is known as electrochemical impedance spectroscopy. And by using this technique, in combination with a free electrode cell setup, it enables me not only to measure the total impedance of my cell, but to measure the resistances of the cathode and anode separately. So this spectrum here shows the data, shows the impedance in the cell after 10 cycles, and you can see that whereas the anode in blue makes up a relatively small contribution to the total impedance in the cell, which is in black, it's the cathode in red, which overall dominates the cell resistance. So in conclusion, electrochemical impedance spectroscopy is a useful technique for analysing capacity fading mechanisms in sodium-ion cells. And the next step in my work is to test the electrical properties of the individual cathode material in order to try and determine the origin of the resistive losses observed so far. Thank you for listening.